Tonight's video is all about freefall, which you hopefully read the chapter in the text or the section in the textbook that talks about freefall. But basically, freefall is when gravity is the only thing acting on an object. And generally, when gravity is the only thing acting on an object, that object has a downward acceleration of 9.81 meters per second squared. And we refer to this as little g. So whenever you drop something on Earth, it accelerates downward at 9.81 meters per second squared. And we can do the same kind of problems with this we've been doing the last 2 days, except now the acceleration we will know is already 9.81 meters per second squared. So basically it's constant acceleration problems, the same equations we've been using, but the acceleration is 9.81 meters per second squared. So let's do 2 examples so you can see what I'm talking about. A brick falls from the roof of a 40-meter building. How long does it take to land? So, if the brick is falling, I already know its acceleration is little g, which is 9.81 meters per second squared. And the distance it travels is 40 meters. So I'm looking for an equation, and I'm going to look on page 46. I don't have the blue sheet with me. 46 in the textbook. For an equation that has acceleration and distance and can give me back time. And this looks like a job for my favorite kinematic equation, you may recall. X equals x naught plus v naught t plus 1/2 at squared. Okay, so not going to show you which ones are 0 except for just crossing them out. So this is going to go by fast. You've done this equation for a couple days now. Alright, x naught. Let's set the origin at the point where the brick is dropped. So I'm going to draw a little picture here. If this is our building, and the brick is dropped from here, then I want the place where the brick is dropped to be the origin, and then the brick falls this way. Okay, so I've defined my origin to be where the point where the brick was dropped from, meaning x naught is 0. It says the brick falls. We can assume that nobody threw it down, so it had an initial velocity of 0. Eliminating that term, 0 times t would be 0. Now we're just left with x equals 1/2 at squared. Okay, I'm going fast because this should be pretty old hat for you by now. Alright, x equals 1/2 at squared. And subbing in the information from the problem, we have 40 meters. Oh, you know what? I'm breaking my own rule here. I should not solve this with numbers yet. I need to get t equals something before I solve this. So let's go to a new slide where I can clean this up and we'll finish solving this. So I got to this point in the last slide, x equals 1/2 at squared. Now I'm going to solve for t. So let's multiply by 2 on both sides. To get rid of that 1/2, I've got 2x equals at squared. Let's divide by a. 2x over a equals t squared. Now I'll take the square root of both sides. And I'm going to come up to the right side now to finish it. Rearranging t equals the square root of 2x over a. Now I'm ready to plug in. T equals square root of 2 times 40 meters. Uh-oh, a. What's a in this thing? Oh right, so on Earth when we drop things, they experience a downward acceleration called g of, not 8, of 9.81 meters per second squared. Okay, so that's our a, 9.81 meters per second squared. Meters per second squared, there we go. Having a rough night. Okay, now if you do t equals the square root of 2 times 40, 2 times 40 is 80, divided by about 10, so that's going to give me 80 over 10 is 8, so t is the square root of 8 seconds. T square root of 8 seconds, which I could simplify to 2 square roots of 2 seconds. By the way, I'm doing this without a calculator, so if you had a calculator, you could have finished this up long ago. And then your answer is whatever 2 times the square root of 2 is. I don't see my calculator near me. But if you 2 times the square root of 2, that's your time. Alright, let's move on. Hopefully not grabbing the calculator didn't throw you off. Just 2 times the square root of 2 is your answer, or the square root of 80 over 10, or the square root of 8. Alright, next example. A helicopter is ascending, that means going up, ascending vertically with a speed of 5.2 meters per second. At a height of 125 meters above the earth, a package is dropped from a window. How much time does it take for the package to reach the ground? Okay, so the package is going to reach 125 meters below where it is. Can I tell you, this problem is going to be interesting in terms of setting up a coordinate system. I'm going to go ahead and do something that's going to seem a little strange to you at first, but I think as I work out the problem you'll see why. I'm going to define the downward direction as positive for my coordinate system and the upward direction as negative. You can do that. You just have to make it clear how you've defined it. And origin. Let's say the height of 125 meters, I'm going to call that my origin. Alright, that means that the box is going to fall 125 meters positively. So positive is now toward the ground. Note my coordinate system. And this is going to be a job for that handy-dandy equation that I do love. X equals x naught plus v naught t plus 1/2 at squared. Alright, so if my height of 125 meters is my origin, x naught goes away. V naught is going to be the initial speed of the package, which is 5.2 meters per second, but it's going up. So, just like the plane was going up, the package is going up if you just hold it out the window. So the package has an upward, and in this case, upward is negative initial velocity of 5.2 meters per second. And my acceleration, since I'm on Earth, down is positive this time, so it will be 9.81 meters per second squared. Okay, I'm going to need a clean slide, so I'm going to move to a new place. I need more space than this, and rewrite all of that. Alright, now I will solve the equation at the top for t. Oh, this could get messy. We got v naught t plus 1/2 a t squared. Alright, I also just realized I do know my distance is 125 meters. Okay, so let's rearrange that equation into something familiar. I'm actually going to bring all the variables over to the right, and I'm going to rewrite it with 1/2 a t squared first, plus v naught t, minus x, so I just subtracted the x to get it over, equals 0. Okay, now let's get rid of that 1/2, make things a little neater, multiply through by 2, a t squared plus 2 v naught minus 2x equals 0. Left out a t somewhere. This is v naught t, 2 v naught t. There we go. Alright, so hopefully this sparks something in the back of your mind, equations of this form. So I'm going to do this a little weird and go ahead and plug in the numbers. I'm going to write this in a different color because I want to emphasize what's happening, and I think you'll see it. 9.81 meters per second squared times t plus 2 times negative 5.2 meters per second minus 2 times 125 meters all equals 0. Let me go to the next slide and rewrite that, and then hopefully we'll all see what's happening. Alright, hopefully this is starting to look familiar. And I'm not saying it because I do want it to be kind of a reveal when we get there. So let me try to get this in a nice neat form. 9.81 meters per second squared, t squared. We all hopefully are clear with that. Let me go ahead and multiply out the 2, 10.4 meters per second times t minus 250 meters equals 0. I don't know if you had to sing this song in middle school, but I certainly did. Negative b, plus or minus the square root, plus or minus the square root, b squared minus 4ac all over 2a. The quadratic formula. That's correct. What's above is a quadratic equation. Negative b plus or minus the square root, b squared minus 4ac all over 2a. So, what's going to happen here is we're going to get a positive time and a negative time. And the negative time is going to be incorrect. For the purposes of kinematics, Unit 1 in physics, time can only move forward. So, let me set this up, and then I think it'd be a good mathematical exercise for you to try to finish it out. So, remember, for the quadratic equation, this is a, b, c. So I'm going to set it up and ask you to finish it off yourself. Negative 10.4 meters per second plus or minus the square root 10.4 meters per second squared minus 4 times a, which is 9.81 meters per second squared, times c, I'm running out of space. Let me write it above it. You'll just know to multiply. 250 meters goes right there, still under the square root, all over 2 times 9.81 meters per second squared. Alright, and if you grab a calculator or do out the math on that, you will have a positive time and a negative time. Only the positive time will be correct. Alright, that was a pretty quick run through of free fall, which was intentional. Free fall is just constant acceleration problems with the acceleration as g, 9.81 meters per second squared. Okay, no, nothing too complex. Same stuff as before, just there's a set acceleration in most of these problems. That's it. There's another video tonight for reviewing for the quiz. That was pretty short because, yeah, it's just a quick review. Not a lot to really go over. Alright, so head over to the next video for your quiz review.